Unmuted.
No, you don't.
All right, everyone. I think we're going to get started. Good afternoon, everyone. Welcome to this week's quantitative seminar. I'd like to begin with a land acknowledgement first. The University of Washington acknowledges the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. And I'd like to introduce this week's speaker, Mark Sorel. Mark is a research scientist in the Columbia River Division at the Washington Department of Fish and Wildlife, where he supports the management of salmon harvest, predation, and hydroelectric dams. Mark received his PhD from SAFS in 2022, where his dissertation work focused on life cycle modeling of Pacific salmon in the Columbia River Basin. And since he's said that his talk here isn't as long as the usual 40 minutes, that he welcomes questions throughout the presentation. So please help in giving me a warm welcome to Mark.
Right, thank you so much, Connor. So good to be here at SAFS with you all. And talking about some of the research and management work that I now do at Washington Department of Fish and Wildlife, and particularly salmon forecasting. And some work that I've been doing to try to kind of improve our forecast accuracy, make it more robust, do the best we can in this arena by regularizing time varying regression models. Okay. I think I can handle it. I think I can get through this today. Yeah. So forecasting salmon returns, the forecasts set the harvest rates, so it's important that we get them right, or that translates directly into, management error, not being able to really meet our management strategies. But it's hard, it's really hard. And some of the biggest challenges, right, is that we're fitting models to time series that are, I would say at most kind of like 75 data points, okay? And we're often using predictors of things like the fish that are siblings of the fish that are coming back this year. So previous year, previous age, but age maturation rates, age compositions change through time. So nonstationarity and relationships in these time series models. And then also there's like a whole slew of environmental covariates that we could incorporate that are correlated with salmon returns. And there's a desire to try to leverage that, but again, 50 or around 50 data points, non-stationary, many predictors. Okay, we're in the realm of like variable selection or model averaging, regularization, something where we're going to have like really overfit models and really bad out of sample prediction. What we're doing 1 year ahead out of sample prediction. So that's the problem. And I'm gonna talk today, gonna use kind of an example as we work through this, just 6 of the kind of, they're Chinook stocks that, it's not all of the Chinook stocks that we forecast, but these are kind of some big important ones. And you can see here kind of the length of the time series that we're dealing with, as long as 62 years or as short as 37. And for each stock, we're forecasting 3 different age stages that we need for the management models. So it's like, we're talking about like 24 different forecasts here. And so how have we typically been doing this as of late? When I arrived in my position a few years ago, we were already using this approach of using dynamic linear models. Right? So dynamic linear models allow the regression coefficients to evolve through time. And I should say the predictor here is sibling returns, especially for Chinook salmon. Got pretty nice age data and sibling returns. And it works pretty well. So this equation on the top is kind of a representation of what I'll call the full dynamic linear model, right? So we're modeling on the log scale. We're modeling returns of fish at a given age and a given year. or we're predicting, we're modeling that's the response. And we have an intercept alpha, and then a slope beta, that the effect is the log of fish that returned in the previous year, previous age, siblings of the response fish. And then some unexplained noise there. And what makes it a dynamic linear model, right, is alpha and beta can evolve through time at random walks. Now, just even this model here can be like too complex, right, for fitting to 50 data points, 37 data points in terms of like optimal predictive performance, right? So the way that we kind of deal with that is we fit every simplified version of this full model and then average them, right? So think about simplified versions, walk through this table here a little bit, right? You can have a constant slope and time varying intercept, or time varying slope and constant intercept, and so on and so forth, including models where there is no intercept, right? We call that cohort ratio because it's just an effect of siblings from the same cohort, or even intercept models, right? Every simplified option is average. That's the approach. About a couple of years ago, somebody in our group pointed out, some of these predictions from the full model are exactly the same as the predictions from simpler models. And of course, that is because, if it's like, if it can't say fit the full model really, it will collapse, right? It's like the time varying thing will just become constant.
Yeah. So why do you do model averaging? Is that like when you don't understand like what the state of the nature of like your model is? Or
yeah, I think so. I think it is a way of dealing with, we don't necessarily have one hypothesis.
Mhm.
And then another way of thinking about it is, let's say like bias variance, trade-off kind of stuff, like, or just more complicated models can be bad at out of sample prediction if they're kind of over parameterized, right? And so by averaging simpler models in, hopefully it deals with that. So it's kind of those two things. Yeah. Okay, so there's this weirdness where the model kind of collapses. I don't know how you feel about that, but kind of you don't want to include the same model twice in an ensemble averaging. That's kind of like a no-no. So we stop even including the full model. That's just like an example of how this approach is kind of a little clunky. Okay, so I'll just show a little bit about how well this has worked on average across those 6 stocks. So here on the x-axis is all those different versions of the full model, and the blue bars are ensembles. One of them is the AICC. We use AICC to weight the individual models when we do the ensemble, and the other one we use kind of like a little retrospective look at predictive performance, which again eats into your time series of for model fitting. But anyways, point here is that the ensemble is definitely not the worst, but it's also not the best, right? So we've got the 3 kind of most complicated models here: time varying intercept, time varying slope, and full model are actually doing better on average across all ages and stocks than the ensemble. So the ensemble works okay, but we've got a few issues here, like taking the ensemble, maybe diluting a little bit this full model, and also this full model's collapsing is a little clunky. Okay, so those are kind of reasons why our approach maybe is perfect. And an alternative would be to just fit the full model with some sort of prior or regularization, whatever you want to call it, that would kind of allow the data to tell us how complex it should be or how simple it should be in the data in the prior. And we just fit one model and everything would be perfect and perform well. That's the hope, right? And that is what I endeavored to achieve. And I think, next I'm going to get into detailing the prior that I've kind of been working on here to try to regularize these DLMs. And we'll get into that. And I will say, I'll just put it out there, I did have conversations with generative AI here about this model, so just throw that out there. Okay, so here is the kind of broad overview, hopefully to give you some intuition into this prior before I show like exactly how it's applied into the model. Okay, so it's called R2D2. I think somebody at least appreciates that. And I think that comes from R squared Dirichlet distributed or something like that. But I like this R2D2. There's a whole family of like shrinkage priors that we've heard of, like horseshoe or things like that. But I like this R2D2 for a couple of reasons. One is it starts by putting a prior on R squared, which is how much of the total variation in the data your kind of covariates explaining. So I think that's really intuitive. And then from there, what it does is it takes the amount of variance that your covariates are explaining, and it distributes them to the covariates based on the Dirichlet distribution, right? So there's kind of like two parts, and they're doing kind of different things, right? The beta on R squared is saying like how much at the global scale do we think all of our covariates will explain this data on an intuitive scale, right? So I'm doing a kind of subtly, a 1-2 kind of subtly pushes it towards simpler, but you could like have a hypothesis about how much it's going to explain and code that in beta. And then the Dirichlet says, based on how you parameterize that, you can have a hypothesis that you think that only a few covariates, like how sparse is it? A few covariates are going to like do all the work, or I think that this total variance budget should be more spread out. So a 0.5 here is kind of like subtly favoring sparsity, but not as extreme as. Okay, and then, so that's the R2D2, and then extending it to a time varying parameter model or a DLM, we need one extra split, and that is the row parameter here, which is going to be the proportion. Wait, go ahead.
So sorry, like, so I guess I'm just thinking like R squared, you're putting a prior on that. I guess like my idea of R squared is like, that's just like automatically generated, like once you have your model and then you compare it against your residuals. So like, how are you getting an R squared before you run a model?
Great question. So that is one of the downsides of the slide is I don't really show it, but in the next slide, I'll show how if you have the R squared and then as a parameter, which admittedly is kind of backwards how we normally do things, and then the unexplained noise parameter, which is going to be like your sigma or whatever you normally have for like your residual variance in a model. With those two quantities, you can then calculate like kind of variance budget for. We'll walk through the next slide. Hope it'll become more clear. Yeah. That's a good question. Yeah. You're getting right at where we're going. But anyways, beyond splitting out into the different splitting the signal budget across the covariates and Dirichlet, we're also doing one further split between it's going to go between like how variable this parameter can be and where it starts.
So do you do this for like each individual parameter?
So this is at the model level. There's one of these for each parameter.
So the operation is that kind of like variable selection stuff?
Yes, an alternative, exactly. It's like a variable selection. Yeah, right. It's an alternative variable selection. It should shrink some of the variables so that they're kind of like out of the model, depending on how like you parameterize it usually. Yep. All right, so this is the second and last slide on this math. I'm glad I'm getting questions as we go here. So, okay, first line here is the observation model, right? We've dropped the intercept, and now we've just got X is our covariate design matrix, betas are coefficients, and epsilon is the unexplained noise with variance sigma squared. Now the betas are going to be allowed to evolve through time as a random walk, right? So beta in pattern T for covariate J is equal to, from the previous time step, plus a little bit of normally distributed random noise. And distributions for the initial value of data for each covariate, and the time step are down there at the bottom. And I'm calling the initial value the static component of the DLM, and then the time steps the dynamics. And the way that prior that I showed on the previous slide, like connects down to setting the variances for the initial value and the time steps is that this is what Connor was asking about. So if you have R squared and your signal variance sigma squared, you can then calculate what I'll call the total signal variance budget, right? So that's like, yeah, how much variance you're going to give for all of your covariates, assuming that your covariates are kind of not correlated, which I'll talk about a little bit later. So you get tau squared, and then tau squared, your signal budget is just getting apportioned out based on these God parameters and the row parameters, right? So we're given covariate. It will say this is how much size, how much of the total goes to covariate J, and this is how much goes to rows, how much goes to the static component, and then for the dynamics, it is the same thing, but the kind of inverse of rho, or 1 minus rho, right? How much of the dynamics of that, or how much of the variance of that covariate goes to the dynamic part. And then we're normalizing based on the length of the time series because a random walk accumulates variance as it goes on, right? So in order to get the variance for one time step, we take the total amount of variance that we're giving to the dynamics and normalizing it based on time series. So that's the prior, that's the math, that's the model. I'll pause for a second. Anybody have any questions or feelings that they'd like to talk about?
So do you necessarily let the process variance for the parameters differ? Like do all slopes get the same process variance?
You mean this term, these terms here?
Yeah, that whole product tau squared.
Yeah, it differs by covariate based on primarily this side of matter, which is usually distributed.
So that's do you allow for the possibility that's the same? I guess why should the time to time variation and the slope on siblings be different than that?
Yeah, it's a good question. Of course, you'd ask that question because in Mars, right, you can have evolutions that covary. And I guess maybe you could set that up here, but you wouldn't be using it. Yeah, maybe you wouldn't use it. Maybe you use what do you call those models? Like a multivariate normal, but logistic normal.
Yeah, well, here, I mean, your betas are, I presume, distributed on the real interval, so you can use you could use multivariate normal just like you have.
Right, that's true. Yeah,
the advantage there is in that simple sibling regression.
Mm-hmm.
There, I would put a negative prior on the covariance because you know that this, right, as you change the slope, you're necessarily going to change the y-intercept. So that's a pretty standard trick that folks will do.
Okay, yeah, that's good. Yeah, that was one thing that I was wanting to go back is check what the R2D2 had to say about the intercepts. Because I kind of went back and forth about whether to just throw them in here, which as I have, or good point. Yeah. Okay.
And my second question, Mark, is do you always force the state to be random walks, or do you allow for a stationary? Meaning there should be an average relationship.
Right. So far, it's just, yeah. But I thought about that, right? There's kind of attractive features to working with stationary processes sometimes, I feel like, but think about it. Yeah. About that. Good question. Yeah, there.
So that total variance budget is interesting. So we do this oftentimes with I've done this a bunch, sort of thought about in a similar way of variable selection where with a parameter that I think varies between 0 and 1, right, the response variable. And then you can basically set that variance budget such that you sort of have essentially you end up with a prior that is sort of uniform on that 0 and 1. But with this kind of response variable, that doesn't make sense. So my question is, do you think about the variance in the data that you see to decide how to set that variance budget?
Yeah.
How do you think about
That's
that?
a good question. I kind of like went back and forth a little bit, right? Because one perspective was to just, and kind of what I did was make the prior favor simplicity and let the data kind of say that it's, how complicated it is. But I think an alternative, right, is you could, code in like, I think that my covariates are going to explain 50%, like, and then I just, something about that, I took pause there at that point, because I felt like maybe it wasn't that simple to say, like, I think that my covariates will explain 50%. I don't know, but maybe it is that simple. Is that what you guys kind of do? It's just like,
It's
or
just,
you make it completely uniform.
over some range, but it doesn't make.
Right. I think people
do that.
do that with this prior. I think a common choice for the beta is 1-1 actually in practice. Yeah.
Which is just the uniform.
Yeah, that which is uniform. Yeah. But I chose to try to subtly favor simplicity.
I mean, it'd be interesting to look at that over time, see if one tendency does that.
Yeah. I was gonna mention that in the discussion, like hyperparameter evaluation is like the next step, right? How sensitive is this, and you optimize that kind of for performance, for predictive performance. Okay, so I've implemented this in RTMB using cost approximation to integrate out the random effects and fitting it by maximum marginal likelihood. It's quick. I can, work through all the retrospective 20 years of forecast performance for all of those 24 stock ages in like a minute or something. So time's not holding back here. Okay, and how well did it work? So in this plot, the dashed line is the ensemble. It's 20 years of one step ahead prediction, mean absolute percent error. Right, so the 20 years of simulating using each of these approaches, having the mean absolute percent error relative to the return, and then the baseline here is that AICC weighted ensemble model that I said is something we've been using a lot in practice. And then the points are relative to that in terms of delta weight. So if you're below the line, you're better. Above, you perform worse. And what we see is that just using the full model, unregularized, tends to perform better than doing this ensemble model on average. And this RPD2 prior kind of performs as well, or sometimes a bit better than that approach. So I found this encouraging. It's not like a huge home run, but I would say these are like meaningful kind of improvements that are encouraging, and I think there's a few other advantages. So encouraged here by these results. I guess on average there was a reduction in 5% error relative to the AICC ensemble for R2D2 DLM.
And this is with just like a frequencist fit. No, this is with no Bayesian.
Right. This is a RTMB maximum marginal likelihood. Yeah.
Okay.
Yeah. Talk a little bit about Bayesian alternative that's available at the end.
Mm-hmm.
Yeah.
So what's with that one green triangle that's way up high?
Yeah. I mean, it worked really bad. Of course, there were some big whiffs in the retrospective. Yeah. I mean,
So if I saw that, I would think that's a model convergence issue. It probably doesn't converge that one model.
Yeah.
Or something.
Yeah, it could be. Yeah, right. It could be, but it suggests to me the difference is the weights between AICC. So with these made weights, what we're doing is we're like, the way I'm doing a 20-year retrospective here, one step ahead performance, we're doing an additional 10 years before the first of the 20th year of retrospective performance, and then using performance in those years to weight the individual models. So you do kind of run out of time series, like fit the models, and something about the weight, I guess, must have been really bad. And I know that for that stock, like if you looked the previous slide that showed performance, the different models across, it was average across the stocks. I have a slide that shows it at the end, you can look at it, but that has it for the individual stocks. Yeah, we get there. Oh, nope. See. Anyways, I have.
Sorry that I broke it.
Yeah, you broke it. Sorry, I didn't fix it. I'm so sorry. Do you think I can find the PowerPoint again?
Yeah.
Okay. So
Mouse should be able to go over to the other screen. Drag the alternation up. There it is.
you can go to slideshow.
Yeah.
Only right this happens at least once on a day, I think.
Yeah. Okay, stop.
Thank you for the opportunity to have that experience. I'm not gonna try again. For that one stock, there was, in some instances, all the models, like all the versions are fairly similar. And then for that one stock, some of them like were really bad. So I think it's probably a weighting issue and the fact that there's some models that perform that. Okay. So just a quick look at a few example trajectories for the covariates, or for the coefficients for a few stocking determinations. So on the top row are the intercepts, and on the bottom row are the slopes. And like in that first column, we can see an example where both the intercept and the slope evolve through time, which is something we were having trouble fitting with the unpenalized version. So that's nice to see. And then I just threw in an example where the intercept kind of became static, or in this case, turned to zero. The slope was dynamic, and then an example where the intercept was really dynamic and the slope was pretty constant. And then for anybody here who's kind of a salmon head, there's been quite a bit in the literature about declining returns at age for Chinook salmon. And so I thought it was interesting that all of the sibling slopes had like a bit of a dip there at the end, which think about like that represents the ratio between the younger age return and the older age. So it's consistent with that pattern. Okay, so moving beyond the simple sibling regression, one of the motivations for this was, can we bring in environmental covariates, right? Something that is really important for some stocks other than Chinook, where we don't have good sibling data, and maybe it can really help with Chinook too. So I kind of fairly quickly threw together this set of 6 really readily available environmental covariates that are included in like NOAA's stoplight chart of they use to kind of give intuition on salmon returns. So it doesn't really matter what they are, but PDO, MEDO, upwelling, NPGO, they're just ocean covariates. I certainly could get more, and that's kind of the next step, is maybe expanding this. But the bottom row there is one of the stocks for your strength, so you can see how correlated kind of cohort strength is each of these covariates. And then the other thing is there's quite a bit of collinearity, right? So correlation amongst the covariates. And yeah, that's about it. In the next slide, I'll show some results for how well it worked to just add all these covariates into the same modeling framework, same prior. But I did want to mention here that in the R2D2 paper, they the way that they calculate things, they account for collinearity in the covariates, right? So like this, it's a cleaner mapping of the variance budget to like the effects because they count for collinearity. I haven't done that here, and I was a bit afraid partly because like covariates are going to involve in each time step, seemed hard, so just kind of yeah. So the not a perfect mapping from that tau term to like the variance explained for the collinearity, but you know, this is forecasting. Let's just see how it works. Let's just see how it performs. Okay, so this plot shows just like the other plot, but now the reference line is the sibling only R2D2 DLM that was performing well relative to the ensemble. The same thing, different stocks, and then the average. So yeah, I'll let you guys look at this for a second. Take some water. But my take on this, right, is most of the stocks showed improvement and on average showed improvement, but these are pretty small improvements, like 2%. There's one stock where it was worse, and yeah. So for me, like, I'm not gonna say throw in those covariates that we have there and this is our new forecasting model because I think keep it simple until proven that complexity is better. But it didn't get worse, which was good. That totally is an outcome that could have happened when you add in a bunch of covariates to a model. And one thing I was happy about is that the fitting stayed really fast. I've experienced in the past when you start adding a bunch of covariates with a bunch of penalized complexity priors, it can kind of bog down a little bit. I think because this is all constrained by R squared, it's pretty efficient. So yeah, subtly encouraging, I guess. There's still more work to do here, but I think maybe this framework will work for exploring environmental covariates use in forecasting. So just a little bit about, I think maybe there was a question earlier, like how much of that variance budget, how did it get distributed out to the different covariates? So on the right there, we have the sibling only model. On the left is the sibling and environmental covariate model. So the sibling predictor, it's the lion's share of the variance in both kinds of models, and the environmental covariates all tended to be a bit smaller. EDO is the biggest. And then I think the other thing that maybe is a little interesting here is that the intercept decreased in this environmental covariate model. The intercept decreased more than the sibling predictor. So kind of makes me think maybe these covariates are explaining a little bit of what was just like a randomly moving intercept. So yeah, I think it's a nice something you can look at in this model, right? Like a kind of a diagnostic. All right, so some takeaways that we talked about, like for the ensemble, for the sibling only regression, this penalized version of the DLM seemed to work as well, or I would say better than using the ensemble approach. So that's encouraging, and I'm going to go back to my group and say, hey, let's take a hard look at maybe using this next year. The environmental covariates, I would say, provided marginal improvement, but the framework, I would say, still shows promise. I think it's maybe more about exploring additional covariates. There's a whole system that could be valued. And then, right, I guess I just said this because the framework is fast and works well with a lot of covariates. I think it'll be a good tool for exploring more covariates, which we have. All right. So I guess I'm a bit of a tinkerer, but I've kind of explored a few like additional aspects, ways that we could take this. The first one feels a little weird to do what I've done, which is additional AR1. So it's take the error in the forecasts, or in the predictions from the previous year, and account for that somewhat in the predictions for the next year. Feels a little weird because there's already like time variant intercept and all that, but I don't think it's unprecedented. And like very preliminary work with that shows that maybe it helps in some instances. Another thing I've been exploring is, so DLMs, right, are to deal with the fact that relationships change through time. And that can be useful for forecasting. It can also be useful for learning about how things change through time. With forecasting, what we really care about is just making that prediction of the next year. So one question I have is, can you do as well as a DLM if you just say, weight your more recent data more heavily, or truncate the time series, which there's a long, before with those DLMs, that's what people did. What year should we start, So I like the DLM framework. You don't have to eliminate some decisions, and it seems to work pretty well, but I'm definitely going to explore this kind of data weighting approach. And yeah, again, early exploration shows in some instances it might do it well or better. Yeah.
I mean, you also don't show the comparison between like all these models and just your prediction is this year's number.
Right, like a true
Next year's the
walk.
same as this year.
Yeah, I thought about using that as the
Are any of them worse than that?
I bet. I bet there's stock agents that are. And I know, I mean, yeah, when you get into this model, it's a good benchmark, really is, because for some stocks, it is better than a lot of other options. Especially if you get average from it, like you get into some of these stocks where you don't have good like sibling relationships. You can try pretty hard and not do better than using the previous years. People don't like to use the previous years because it feels too simple.
Yeah.
Yeah. But yeah, that's one of the things that we're trying to focus on more is the decisions about what forecasts to use. Maybe you can relate to this. Get made in these like technical committees, semi-technical committees. And one of the things that we're harping on lately is just in order to inform those decisions, do the retrospective analysis of performance at a minimum. Doesn't even always get done. Anyways, okay, and then the last thing to explore, I think Sager mentioned it, is what is the sensitivity to different hyperparameter values, and does it even maybe make sense to try to tune those using like a cross-validation of some sort for their predicted performance? Again, you get into the issues of like, you only have so much data, so you're talking about trying to do leave future out, cross-validation, but I think it's worth a shot. Yeah.
Like with the hyperparameters, is there potential for like neural nets there to just like search across those vast parameter spaces?
Yeah. I mean, probably. Yeah, but at what point do you just farm the entire thing out to the neural net? I use the DLM framework, and that's a good segue into my next slide. So future directions, right? One is apply this to other species. I mentioned for some of these stocks like coho, we're relying more on environmental covariates already because they don't have the good sibling relationships. So this may really help. But the other thing is benchmarking this against some other things besides the DLM ensemble, and that could include neural nets or boosted regression trees, random forests, these things that, I mean, they can account, right, for nonlinear relationships and probably I don't even understand how they account for, dynamics. And I think that's maybe the point. But again, really small data. That's the thing that you have to keep in mind. Right? I think neural nets can struggle just because 50 data points. But definitely machine learning models are worth exploring. And one thing we have used is a big model average of auto arena models with different covariate combinations. And it's a little slow. It's takes some time to work through, but it does perform pretty well. So we've been using that for Coho. And then I said I was going to mention a fully Bayesian alternative. There is an existing R package called shrinkTVP, which implements shrinkage priors on time varying parameter models. So I definitely want to check that out, see how it compares. It's not the R2D2, it's like a additionally independent horseshoe where there's other option priors. So I don't know how well it scales a lot of covariates, but it's certainly worth investigating. And I got an email from Jim Thorson this morning that apparently his new DSEM package, I think, also could maybe be thrown at this kind of problem. So maybe we'll explain that as well. All right, I think that's all I've got. Yeah, thank you. For being here. If you have questions, yeah, acknowledging our friend the flawed. And yeah, I do have a GitHub repository for an R package that has like the established method that we use, and working on adding in this R2D2 prior, probably a little bit in there, but we'll continue to update that if you want to follow along. So, yeah, thanks.
I'm not seeing any new questions online. Are there any final questions for Mark? Yeah, I'll let you.
Yeah, but you saw behind Sarah. We'll let you go first.
You can probably just tell me to go read the paper, but
Read the paper.
you briefly mentioned how that covariance is accounted for in the Zang. Did you mention that?
Yeah, I really haven't have to tell you to go read the paper.
Yeah, fine.
But yeah, I mean, there's some sort of matrix multiplication, I think, where with, I think it's like it involves the design matrix, maybe the inverse of the design matrix and the coefficients. And with that, you can you can calculate how much, which is pretty cool. I mean, I feel like I have a little intuition in my head, but I can't tell you how it's actually done. But hopefully you saw the reference or you can find it. Or you need to, for sure. Yeah. Okay.
Yeah, so
Goes first.
Go ahead.
Okay, so that's a simple question. How precise is this estimate of returns?
Yeah. So maybe I'll try to get to that slide that this was what I was trying to get to before and I exited the PowerPoint. So these were the ensembles and the individual models, and the DLM was a little bit better, but and this is me. So I guess when you say precision, I think of MAPE as a measure of its forecast accuracy. So it is a measure of precision. And actually, increasingly, I use that sometimes to derive. I use like performance and retrospective analysis to derive like confidence intervals for these things, rather than like model estimates. And often that's because I'm adding a bunch of ages together, so either I can do full Bayesian or use the delta method, or just use 20 years of retrospective performance. I think it's kind of how like machine learning models calculate prediction intervals, right? It's just like, well, how well will it do? So, but yeah, so it varies by stock quite a bit. Like for spring Chinook, we're in the 25% error range on average, and pretty good. But for BPH, we really struggle with that one. We brought all the time, on average, 50%. Yeah, bummer, but so far hasn't been a way to improve. So, want to collaborate? It's kind of fun.
But Matthias, were you asking about, I thought you were asking about the precision of the actual returns.
Yeah, I was. That's a good idea. But in absolute terms, I would just say, like how much they vary in terms of confidence interval.
Right. Precision of the absolute. I mean, we generally don't really know because it's like quite. We don't really work on that. It's not really, the management frameworks aren't really designed to use it. They're definitely not designed to use it, right? They rely on like point forecast. That's how you determine if you met your or a point estimate of the return, whether you measure
Mhm.
allowed rate or not. And um,
Hmm.
yeah, I mean, like, I try to be forward thinking and say like, okay, well, if I produce it, then we can figure out how to use it. But yeah, it's a little unclear. It's a little like sticky in the way that we do the run reconstructions to get these things. It would be a little awkward, but it could be done. We use dam counts. You don't really have you would need uncertainty estimates on a lot of your inputs. You sometimes don't have.
I see.
Yeah, but that's a great question. And certainly that contributes to the forecast error.
Yeah,
Like we're forecasting
Yeah.
this number, right? Yeah,
Hmm.
which isn't even, estimating layer. Yeah, you can use management stocks. Anyways, okay. Sarah.
Yes, okay, cool. So I mean, it's the raw parameter, right, that allocates between the static.
Static and linear.
Yeah, so. So I have this like general idea as an ecologist that if you could just get the right covariate or set of covariates, which probably don't even exist, then you wouldn't have a time varying relationship because the relationship would be sort of ecologically set, right? It's like, yeah, I mean, outside of like some microevolution or something like that, like this is really determinative of how this population functions. And so I guess my question is, when you look at environmental covariates versus sibling predictors. Do you find differences in those row parameters? Because I would expect there would be more allocation to static, a static coefficient with the environmental covariates because it's a little more mechanistic. A little bit more, not that.
With the environmental,
Yeah.
Such a good question. And it brings up something that I'm glad I'm gonna have an opportunity to say. When I looked at that, I was a little disappointed in that there wasn't that much deviation from prior value. So it seemed like maybe it was harder to estimate those splits. And I should have included a lot of that so we could have looked and seen if there were some of those patterns. I mean, there was a little pattern, they weren't like all pegged right at the prior mean. But I guess all I can say is that gives me a good nugget to look at when I go back to this. Yeah, it's an interesting hypothesis that with the more mechanistic, they might favor more static, or more complex might favor more static. And maybe that's something that could be encoded in the prior some way. I mean, certainly it could.
Yeah. I think Or,
or make that prior more vague and see if it's.
yeah, right. That's, I guess, what I'm thinking. Let it sort itself out. But I think you're right. It's probably actually really hard to put it out.
Which is disappointing, right? Because.
But I think the other issue is that right here in theory, you could use these on what is essentially a nonlinear relationship. Right? The slope is changing because it's technically not linear.
Right. Yeah.
Which I think a lot of these covariates are in non-linear effects that we don't.
Right.
Oh, yeah,
we see it this year that it looks negative because of the place that we are at in the covariate phase.
Or we only get it's this, and then we get 2015 or some bizarre year, and all of a sudden we're way outside.
Right.
Mm-hmm.
Right. Yeah. I love that. Yeah. I had a funny exchange with a colleague who was like, "I'm really interested in looking at nonlinear relationships with covariates and forecasting," and I was like, "That's what I'm working on right now." And I realized it meant the other nonlinear, but not changing through time, but changing across the parameter values. So there's two different ways that you can do it, maybe together. Yes.
Yeah, I had two questions, and I'm sorry, I know you were talking about this for like a lot of the presentation, but I think one question is like, what does sibling relationship mean? And then my second question is like, I think I got a little confused because you brought up like you were using priors and like to build this model, but then it ended up being a sort of like you said this is a frequentist model.
Yeah.
So I guess Maybe I was just like confused, like, is that, what sort of setup is that?
Yeah. Yeah, okay, so I don't actually know the correct terminology there, but maybe you can call them penalties and this, it's kind of like pseudo Bayesian, this kind of marginal maximum likelihood, but maybe it'd be more accurate to call it a penalty than a prior in this instance.
Penalized likelihood.
Penalized likelihood, yeah, R2D2 penalty. And then there's
Whenever I've tried to do that in reality, the reviewers told me just, why don't you make this basic?
right. Yeah.
I give it prior.
It's a perfect segue because one more thing on the previous question that I thought of. If I explore that shrink TVP, which is out of the can and fully Bayesian implementation, I feel like there's a better chance that it would be able to estimate the kind of, well, it doesn't have a row parameter, but like separate the dynamic and static. So we have better luck with that.
I do think Mark's point about that's really interesting. Be interesting to look at years with similar conditions and see whether your time specific betas look similar in those years. There's
probably something there.
Yeah.
And it would probably be helpful to like include a lot of stocks if you did that analysis, because get around a little bit the time series issues.
Yeah, that's another thing that occurs to me is that you actually have 6 times whatever 50 years here, right?
Right, in multiple ages, yeah. So yeah, I think you kind of have to work in multi-stock stuff to make generalizations. Yeah, I do remember the other part of your question now. It's about the sibling cohort thing. So, right, so like spring Chinook, returning to the Columbia right now. When we do our run reconstruction, we'll estimate how many of them were aged 3, 4, and 5, right? And the ones that are returning at age 4 this year, was it 2026? They were born in 2022 and entered the ocean in 2023. And the age 3 fish that returned last year were born the same year, right? And they hit the ocean in the same year. And since when we're doing the forecast last winter, we already knew how many age 3 fish came back. That tends to be really predictive of how many age 4 fish came back this year. Because they're same parent, like, same cohort, same ocean experience until the 3s come back.
How do you know they're from the same parent?
Well, not individual parents, but the same generation.
Thank you.
And same freshwater conditions.
Same freshwater conditions. There's a lot, yeah. So it tends to be.
Gotcha.
Yeah.
Thank you.
Yep. All right. On scores, any other questions?
Not online, so, well, thank you all so much for coming.
Thank you.
Thank you again, Mark. It was
Yeah.
wonderful.